I hope it's likewise. Okay, you enjoy attending my class on a Thursday and Friday. Oh, we are up. Okay. Good afternoon. Okay. I have not a clue what the grades are yet. We are still marking. Okay. I have a quick look. Okay. It seems to look better. Okay. It seems to. Okay. But let's wait and see. Okay. Right. So today, where we finished off last week, I'm going to go through principal stress and Mohr circle. So I'm going to recap what you learned last week if your mind of state is okay. Okay. So last week we finished off with the compound loading structure, and also we look at the element, right? We start drawing elements. So last week one of the element we construct or something like this. Okay. So then we had our tutorial, and the tutorial we talk more about the term test. Okay. And then we briefly look at material behavior. Okay, we briefly look at mechanical properties. Okay, so what does all these properties means? So last week where we finished off is the factor of safety. Is it ultimate strength divided by allowable? Okay, or is it U strength divided by allowable? So the textbook highlight that it is the ultimate strength divided by the allowable. Okay, and I mentioned that this is true, right? And this is true, and true is only true if we are dealing with what? Brittle material. Okay, why brittle material? Because in brittle material, right, if you look at the yield and the ultimate, there's not a lot of difference. Okay, so is very similar. Okay, then where else make attendance worth 100% or avenue cheeky sort? So where the factor of safety for ductile material, it is the yield strength divided by the allowable. This is because we use the yield, okay, not the ultimate, because there is quite a significant difference between the ultimate and the yield. So if a ductile material, if you use ultimate, you go into plastic deformation. Okay, so as an engineer, okay, you should know when to use what. Okay, that one is clear. Now the next thing comes. If you look at any of these tests, I repeat again, if you look at any of these tests, the listing is either is always unidirection. Okay, so all these tests, okay, so all this data, okay, will carry out. So data obtained in unidirection. So in the context over here, what do I mean by unidirection? It is one direction. Okay, it is one direction only. So some of you might ask, Eugene, what are you trying to drive over here? Okay, so what I might go drive over here, or what I'm going to emphasize over here, is the critical component of Mohr circle. Why do we need Mohr circle? Okay, let's watch over here. So if you look at any of this handbook, okay, what you see is the tests will either carry out in one direction, tension, okay, or compression. So none down here is in compression. You can see no values down here is in compression. When you see data like this, you can make an assumption that tension and compression have the same magnitude, okay, but not for shear. Shear, you cannot assume the shear stress is the same as tension. No, that will be suicidal. That will be like a big no-no. Okay, right? So if there's only one value given, you can assume, make the assumption that tension and compression loading are the same. But usually, in general, okay, in general, it's pretty risky. Okay, but in general, we will say that the test in the strength in tensile, right? Or the stress, sorry, the stress is not tensile. The stress in compression, okay, is about 1.3% of that of tensile. Okay, So materials can withstand higher compression load compared to tensile. Okay, so now we are looking at ultimate strength. Then you look at a handbook. Okay, any material handbook you can get. Okay, you can see. Then we have data known as tension. Okay, yield strength, and then we're given shear. Okay, now these tests are done separately, unidirectional. What do I mean by unidirectional? So some of you have taken 3C, I did mention before. So let's look at tensile. So in tensile or in tension, right? This is the material, right? And then they pull it. Okay, so you have a load P and a couple P prime, and then this over here is the area. Okay, so if we have X, Y, and then rotation in the Z, what we will see that stress in the X direction is equal to P divided by area. Okay, divided by area. Real straightforward. Okay, you all know. Okay, so this is what we mean by unidirectional. Okay, one direction only. Right. So from here, you can see data given in tension only, and then a few done in compression. Compression tests are not easy to carry out. Okay, need a lot of preparation. So that's why you see tensile value that is very common. Okay, that is the only reason. Right now, so if you look at this tensile test, right, the data is in unidirectional. Okay, so let's look at an example that we have done last week, or we can look at an example that we've done last week. Let's look at this example. Yeah, let's look at. So this is this loading condition. Yeah, so let's look at this loading condition. Right. Then from there, right, we came out with an element. Okay, we came up with. I'm going to. Okay, we're just going to look at example. We came up with this element. Okay, we came out with this element. Okay. Now, question for you guys. Question for all of you. In fact, not you guys or everyone, anyone. If we were to look at element, probably some of you are like really pissed off with this figure. So, question for you guys: is the loading condition between the figure at the top and the one at the bottom the same? Anyone? Are the loading condition the same? Obviously, no one answered because it's very obvious. It is not what? It is not the same, right? So now the scary thing is this. Then how come if it's not the same, right? It's not the same. So the uniaxial and the one that the example that we had in question 8.5 is not the same. Then how in the world did we link, okay, the yield strength, right? The yield strength over here. How do we link the yield strength to our stress state on our element, right? On our element to select the material. How do we do that? Okay. So there has to be a bridge. Okay. There has to be a common denominator down here that we could link a uniaxial test or uniaxial data with actual loading data. So we have to link uniaxial, okay, uniaxial data or material data to the compound loading, okay, to the compound loading, okay, by using Mohr circle. Okay, we have to link it. So you guys are like, why is that? Okay, why is that? So why principal stress? Okay, so if I were to draw, okay, if we were to draw, right, the element. So we have an element down here, right? So this element will have. I'll draw a brief transformation. Okay, so this is our x and y. Given the stress state, right? This will be our P over A, and this will be our P over A. Okay. So this will be our point. Don't worry, I'll go through Mohr circle. Okay, this is our point X, and this is our point Y. Okay. So we start drawing Mohr circle. So when I sketch, this is just a very brief sketch. If I just sketch Mohr circle. So this is our point X. This will be our point Y. Then we consider our circle. Okay. So at this point, this is our stress U. Right? That's how. So IE, when the shear stress. So what would be before I go on? Okay. What do I mean by principal stress first? Okay. So before I go on, so what do I mean? So principal stress. Okay. Are stresses that have zero shearing stress. Okay, zero shearing stress. As you can see, the structure that we do for uni XL test. Okay, there's no shear. Okay, so what you see over here, right? What you see over here, all these stresses over here at these 2 points are known as our principal stresses. Okay. Now coming back to the context on where we are in this value, if you see any of this value, because it is uniaxial direction, okay, this entire value or any value you see down here, sorry, in tensile and in except shear, okay, these are all your what? Principal stresses. Right? These are our principal stresses. Okay, so what you see, this is U strength. Okay, in solid mechanics or in structural analysis, it is our principal stress. Why our principal stress? Because the shearing stress is equal to what? Is equal to 0. Okay, so now over here we have tensile stress. Okay, so if I draw our transformation, so these are X, Y, and Z, right? So these are known as our direction. And if you look at the element, we have a shear and we have a what? Tensile. So if I'm going to call this X and I'm call this Y, right? This is just a sketch, by the way, okay? So this is so this is our Mohr circle. Okay. Sorry, I should write better. Okay, so this is our Mohr circle. So this is our normal stress. Okay, just normal stress, not stress X. Normal stress, and the vertical line is our shearing stress. Okay, so from here we can see that we have a so stress Y. So I'm just going to roughly say that this is our stress Y value. Okay, and this is our shear. Right, this is our shear. Okay, so we have point X, point Y, and then we have another point Z over here. So point X, where we are is the element rotate clockwise in shear, anti-clockwise in the bottom part. So we have at point X, they have 0. Okay, we have 0 normal stress, but the shear is going to generate a clockwise rotation of our element. I will elaborate on this more. Okay, so this is one value. Okay, so this is point X, and point Y is tensile. Again, this is not to scale. Okay, and it's rotating anti-clockwise. So this is our point Y. Okay, then from here, I'm going to sketch out a circle. It's not perfect. This is our Mohr circle. Okay, so this is our 2D Mohr circle. Okay, and if we go into 3D, which we'll do next week, okay, we have another point down here, which is our Z